This is part 4 of the series Applications of Differentiation, and in this session we're going to start out with a very important concept in calculus overall and specifically related to differentiation, and that's the idea of extreme values, maximums and minimums. Determining the behavior of a function is a really important thing, and there's many branches of calculus that devote lots of energy to that. So we're going to talk about what is an extreme value and how we're going to find it. So first, the definition of extrema. If f is a function defined on an interval containing some point c, then we can say that f of c is the minimum of f on that interval if f of c is less than or equal to f of x for all x in that I. What that's simply saying is that as you move along the x-axis between a and b, if f of c, this value c, is less than any other x value on that interval, then this is a minimum point. And the opposite, if f of c is the f of c is the maximum if f of c is greater than any f of x for all x and I. So here we have a maximum value because it's greater than any value along the interval from -1 to 2. So we have an instance here where this is a minimum, this is a maximum, because that value at our c value of 0 is less than any other function value at any other x coordinate in that interval. This is a maximum because it's greater than any other value on that interval. Now we would say that one extreme value is an extremum, and these two extreme values are extrema. Extrema is plural, extremum is singular. And now let's move on to a theorem that directly relates to this. Now this theorem is called the extreme value theorem. What it says formally is if f is a continuous function on a closed interval ab, then f has both a minimum and a maximum on the interval. So if you look at this function, it's on a closed interval from -1 to 2, you can see that this function is going to have a value that's less than or equal to any other value in the function and a value that's greater than or equal to any other value in the function. Let's say, on the other hand, that this point is not defined in the function. This would then be an open interval from -1 to 2 non-inclusive. In that case, there would be no maximum of this function, because no matter which point you picked, there's always going to be one more point a little closer to 2 that is greater than the one before, and by the definition of an extreme value, you could never reach the maximum value. You just keep on going, getting closer and closer and closer to 2. And so this function would not have a maximum if it were discontinuous. Likewise, if it were discontinuous at a minimum point down here, the function would not have a minimum. So on an open interval, a function need not have maximum and a minimum, but on the closed interval, it must have a maximum and a minimum, according to this theorem. So let's take a look at some more consequences of this idea. So let's look at a function that's defined on an open interval. In this case, this function would not have any absolute maximum or minimum, but it would have what we define as a relative maximum and a relative minimum. That is, a maximum within some specific interval on the graph of the function. So the formal definition of a relative extrema is, or of relative extrema, is if there's an open interval containing some value c on which f of c is a maximum, according to our definition that we gave before, then f of c is called a relative maximum of f, or f has a relative maximum at the point c, f of c. So given that this is an open interval, this value is not an absolute maximum because you can clearly see there are values that are greater. But if we choose an interval containing this point that doesn't include these values, this would be a relative maximum on that interval, say -1 to 2. Likewise, this would be a relative minimum, and a relative minimum is if there is an open interval containing C on which f of C, this point, is a minimum, then f of C is called a relative minimum. So we can define relative minimums in terms of open intervals, where before we had absolute maximums and minimums on a closed interval, which is what we were talking about with the extreme value theorem. Let's go ahead and investigate some more behaviors of functions at their extrema. What we want to do here is we want to evaluate the value of the derivative of this function at the point 3, 2 and see what's happening at that point. So before we differentiate, I'd like to simplify this a little bit. And x squared divided by x cubed is x to the -1. You subtract the exponents. So what we've got here is f of x equals, pull out the 9, and that's x to the -1. X squared divided by x cubed is x to the -1. -3 divided by x cubed is, since there's no x value up here, we're just going to change the sign of that and bring it up to the numerator. So this is minus 3x to the -3. And now we can just use the power rule on this. So I just divided both terms by x cubed is all I did. So f prime of x equals 9 times -1 over x squared plus, because it's -3 times 3, 9 over x to the 4th. Okay, now we're going to evaluate this expression at that value. So we have 9 times -1 over 3 squared is 9, plus 9 over 3 times 3 is 9, times 3 is 27, times 3, 81. So when we multiply these out, we get -1 plus 9 divided by 81 is just 9. So this is 9 over 9, which is just 1. -1 minus 1 is 0. So this derivative, the derivative of this function at 3, 2 is 0. And if we take a look at a graph of this, what we're actually dealing with at 3, 2 is the tangent line to the function is horizontal. Now, remembering that the derivative gives us the slope of the tangent line, you can see that the slope of the tangent line from this point all the way up to this point is positive. So the slope of the tangent line is positive, therefore the function is increasing. When we get to 3, 2, the slope of the tangent line is 0, so the function is no longer increasing. And you can see that just past that point, the slope of the tangent line is going to start turning negative. So what that tells us is the function is going to start decreasing. So we can start seeing that when the slope of the tangent line of a function is 0, we're going to have an extreme value. In this case, we're going to have a maximum. And let's take a look at this a little bit more formally. What we've just uncovered here is a new term, and it's called a critical number. And it says, let f be defined at C if f prime of C equals 0, which is what we found in the last example, or if f is not differentiable at C, then C is a critical number of f. And an extension of that is relative extrema occur only at critical numbers. If f has a relative minimum or relative maximum at c, then c is a critical number of f. So we've just discovered a way for us to find the extrema of functions. That's all we have to do is take a look at the derivative, and if the derivative is either 0 or undefined at any particular point, that point is an extreme value. And so let's see how this works in practice. So what we're going to do is we're going to find the extrema of this function on the interval -1 to 2. So as we just discovered, we're looking for critical numbers, which requires us to take the derivative. So f prime of x equals 4 times 3 is 12x to the third minus 12x squared. So here we're going to factor out a 12x squared. So 12x squared, that leaves us with x minus 1. And since we're looking for where this value is 0, let's set this equal to 0. We know 1 by the zero product rule is 0. So x is going to equal 0 and x is going to equal 1. If x minus 1 equals 0, x equals 1. So we have 0 and 1 are our critical numbers. Now to find our extreme values, we're going to have to do a little bit extra work. Because this is a closed interval, we may have an absolute minimum and absolute maximum on that interval. So what we're going to have to do is we're going to have to evaluate the original function at our critical numbers and at our endpoints. So what we're looking at is we want to find out what is f of -1, what is f of 0, what is f of 1, and f of 2. So putting these into our calculator, we see that f of -1 is going to be 7, f of 0 is 0, f of 1 is -1, and f of 2 is 16. So it's clear at this point that 1 is a minimum, which is one of our critical numbers, and our max is an endpoint. So this endpoint 2 is our maximum on this interval, and -1 is our minimum. So we can say that -1 is a minimum, and 16 is our maximum. And those are our extrema on that interval.